This is the third section of chapter 1 on number theory, and this is on modular arithmetic. Now, modular arithmetic is basically the remainder you get when I'll underline the word remainder, you get when you divide an integer by a number which we're going to call the modulus, by the modulus. So it's the remainder you get when you divide by the modulus. Now the modulus can be any integer, and we often shorten it to m, or mod m, and m is this modulus. It's that number we're dividing by. So let's have a look at an example. So let's say I had 16 and I want to write 16 in mod 12. We just shorten it to mod 12. So basically, what is that? When I divide it by 12, what's the remainder? And it needs to be a positive remainder. And that remainder is 4. I'm just going to put equals for now, equals 4. So what we say is that 16 is congruent to 4. Okay, so I'll just write that down. 16, what those three lines mean, is congruent to. You can basically think of it as meaning it's the same number. Is congruent to. 16 is congruent to 4. What does that mean? It basically means they have the same remainder. They have the same remainder after you divide them by 12 when divided by 12. Or you could say under mod 12 or modulo 12. That's another way of saying it. They all mean the same sort of thing. Okay, right, let's try another one. Let's go for negative 5. What's that going to be in modulo 7? Okay, right, so when I divide that by 7, what's the positive remainder? Well, I can write negative 5 as negative 1 times by 7. So the positive remainder will be 2. So I can say that negative 5 is congruent to 2. They both have the same remainder. Now I can generate other numbers which have the same remainder by adding or subtracting multiples of 7. Yeah, they're numbers that are all going to have the same remainder. So if I add 7 to 2, I'm going to get 9. So that's congruent. I can add 7 again, 16. I could take away 7 from the minus 5. So that gives me minus 12. So all of these numbers are congruent to one another. They have the same remainder under this modulo 7. And that remainder is 2. So I'll just put here, we can find other congruent integers by adding or subtracting multiples, let's call that, of m. So the k is just going to be multiples, and the m is going to be what our modulus is. Right, so now we understand what modular arithmetic is. Let's have a look at some rules. So the first rule here basically says If a number is congruent to 0, which basically means the remainder is 0, it can be divided by the modulus. So here's an example. Let's say that 35 is congruent to 0. Okay, that means that 35 can be divided by its modulus. So its modulus could be 5, couldn't it? Because 5 divides it exactly, or it could be 7, or it could be 35, couldn't it? Yeah. So if we were to write, for example, 35 is equivalent to 0 or congruent to 0 under mod 7, for example. So whenever a number is equivalent or congruent to 0, it means that it can be divided exactly by its modulus. Basically means there's no remainder. Second one basically means that any number is congruent to itself under a particular modulus. So here's an example. Let's say we have 7 is congruent to 7. Well, that could be under any modulus. Would it have to be a modulus greater than 7? So let's say mod 12. Every number is congruent to itself. Here we can write modulus either way around. So let's say I had one number congruent to another under a certain modulus. I can write it the other way around and it's still true. So here, for example, where I wrote 16 is congruent to 4, I could also write 4 is congruent to 16. It's true as well. Then the next rule here basically says if you've got one number congruent to another. So let's say I've got -5 is congruent to 2 and 2 is congruent to 9. So -5 is congruent to 2, 2 is congruent to 9 under mod 7. So I'm just using these examples here. Then it means that the first number is congruent to the last number. So -5 is congruent to 9. Okay, that's basically what that rule means there. Right, now we'll move to these rules down here. Now I've added a little bit here. I've added 2 more extra bits of information that we need. So this just applies to these rules here. So A and B are congruent, C and D are congruent. All of the letters here, A, B, C, D, M and N, they're all integers. And in particular, M and N are both positive integers. So in other words, the modulus is only going to be a positive integer, and here n, the powers, are only going to be positive whole number powers, so no fractional powers, no negative powers. So let's look at the first rule here. So A and B are congruent, C and D are congruent, which means if I add A and C or subtract A and C, it's going to be congruent to B and D. So here's an example. Let's say I've got the numbers under modulus or modulo 7, 2 and 9 are equivalent under mod 7. Yeah, and we know that because 2 plus 7 is 9. And 2 other numbers which are congruent are 5 and 12 under mod 7. Now this rule is telling me that if I do 2 plus 5, that's going to be congruent to 9 plus 12 under mod 7. And let's just check to see if it is. Well, 2 plus 5 is 7, which is 0 under mod 7. And then 9 plus 12 is 21, which is also 0 under mod 7. Okay, so that describes this rule here, and we could prove the same thing if we did a subtraction. So I don't know, 5 minus 2, 12 minus 9, that would give us 3 on both sides, and 3 would be equivalent to 3 or congruent to 3 under mod 7. Now we can do the same thing here with this multiplying, so let's try that out. So using the same numbers again, A, B, C, D, we multiply A and C. So it's saying that 2 times by 5 will be equivalent to B times by D, 9 times by 12, and the mod 7. So we'll see if that is true. So the 2 times 5, that's 10. And the 9 times by 12, that's going to be 108. So let's see what they are under mod 7. So the 10 will have a remainder of 3 once divided by 7. Now let's see 108 divided by 7. That is 15 times by 7, which is 105 with a remainder of 3. So it's true, well, for those numbers, but in general, this rule will also hold. Next rule down here, basically we can multiply both sides of a congruent relationship by the same number. So let's go back to here again. If I've got 2 and 9, if I multiply both sides by 7 or 8 or 9 or 10 or any number, the relationship still holds. And then the last rule down here is if we do the same power to 2 congruent numbers, A and B, that rule still holds under a certain modulus. So here, for example, if I did 2 cubed and I did 9 cubed, this relationship would still be true under this modulus 7. Okay, so on this question here, we want to decide which of these statements is true. So basically, it's asking us, do each pair of numbers, or does each pair of numbers, each pair have the same remainder, under the modulus that's been given. So do they have the same remainder? So there's lots of ways of working it out. Another way maybe is to show that the difference between the numbers is a multiple of the modulus. So let's do it both ways. So 24, right, what's the remainder when we divide that by 5? So this can be written as 5 times by 4, which is 20, plus 4, so it has a remainder of 4. 9 can be written as 5 times by 1, also with a remainder of 4. So that shows that the statement is true. Another way of doing it is to say, right, the difference between these two numbers needs to be a multiple of 5. And it is a multiple of 5. It's a multiple of negative 3 times by 5. So that proves that they are congruent to each other. So this statement is true. So maybe if I was writing this question, I might do it this way. And then I would write 24 is congruent to 4. 9 is congruent to 4. Therefore, 24 is congruent to 9. So this statement is true. And we'll do the others in a similar way. Right, so negative 5 under not negative 5, 5 in modulus 8 or mod 8 or modulo 8 can be written as 8 times by 0 plus 5, so it has a remainder of 5. Negative 11, now remember the remainder needs to be positive, 8 times by negative 2, which is negative 16, plus 5. So that proves that they have the same remainder. So 5 is equivalent to 5 in mod 8. Negative 11 is equivalent to 5 in mod 8. So that shows that 5 is congruent, I keep saying equivalent, congruent to negative 11 under mod 8. So the statement is true. We could have also said, right, is the difference between the numbers a multiple of the modulus? So to get from 5 to 11, we subtract 16, and the modulus divides negative 16. So that's another way of proving it as well. So let's go on to C for congruent to 17 mod 2. So we're going to see if this statement is true. Right, so 4 under modulus 2 is equal to 2 times 2, no remainder. 17 is equal to 2 times 8 with a remainder of 1. 4 is congruent to 0 in mod 2. 17 is congruent to 1 under mod 2. So they're not equal to each other. So 4 is not congruent to 17 in mod 2. The statement is false. Another way we could have done it is saying, right, how do I get from 4 to 17? Is that a multiple of 2? So to get from 4 to 17, we add 13, and 2 does not divide 13. So that's also another way of showing that the statement is false. So given that n is congruent to 10 in modulus 3, write down 3 possible values of n. Well, the first thing we need to do is to find out what's the remainder of 10 when we divide it by 3, and we want to find other numbers that also have the same remainder. So what is 10 when we write it in mod 3? Well, 10 is equal to 3 times 3 plus 1, so that's a remainder of 1. So we can write down any other numbers which have a remainder of 1 when we divide them by 3. So any integers that have a remainder of 1 when divided by 3. So here's just a few. So 13 has a remainder of 1. So one more basically than a multiple of 3. 22. 31. Let's do a negative number. Negative 2. One more than a multiple of 3. So let's say negative 30 is a multiple of 3. One more than that, negative 29. So any value that's one more than a multiple of 3 has a remainder of 1, just like 10. Part B, the greatest negative value of n. So numbers just below 0, or a negative number just below 0, first number I get to just below 0, which has a remainder of 1. So maybe one way of doing it is to say, let's pick one of the numbers we've got. So it's 10. I'm just going to go down. 7, 4, 1, negative 2. Okay, so my answer would be negative 2. So all I did was pick a number that I know, that remainder, and I take off multiples of the, or took off the modulus, keep taking off 3's, and that's the greatest negative number that I can get. And part C's, the value of n contained in the set 0, 1 and 2. So which one of those has a remainder of 1 or is congruent to 1 in modulus 3, and that's going to be the number 1. Yeah, because 1 is 0 times 3 plus 1. It has a remainder of 1. So my answer is going to be the number 1. Okay, so this was a fact that was given right at the beginning in the introduction. We're going to prove it here. And this is to do with the differences between two congruent numbers being a multiple of the modulus. So we'll start this proof off. Right, so if A is congruent to B, what that means is that, well, let's put in modulus M, because that's important. Then what that means is that the difference between those two numbers can be divided by the modulus. We were doing that before. So we've got two equivalent numbers, congruent numbers, under a certain modulus. The difference between those numbers can be divided by the modulus. Now we could rewrite that and say, well, actually, the difference between these two numbers is a multiple of the modulus. Okay, so the difference between those two numbers is equal to a multiple of the modulus. And we were doing that before. We were multiplying the modulus and adding it and subtracting it to one number to get another number, because that difference is always the same. Right, so we've set that statement out. We're going to do the same with B and C. So if B and C, I suppose I should put if here, if B and C are congruent under modulus M, then that means that M can divide the difference between those two numbers, which also means that the difference between the two numbers is a multiple, let's call this multiple L, of the modulus. So I'll just put here where K and L are, they're going to be integers, because it's just like a multiple are integers. So they're elements of the integer set of numbers. Now the next step is I'm going to add together these two equations here. So adding Km equals B minus A and Lm equals C minus B, I'll get this, Km plus Lm equals B minus A plus C minus B. So we'll simplify it and factorize it. So I will get M K plus L is equal to, now what's going to happen here is that the B will cancel out, B minus B, so I'll have C minus A, C minus A. Now this is very similar to one of these statements here, so we're going to work backwards, and what this statement is saying is, well, if you multiply the modulus by something to get the difference, then the difference can be divided by the modulus and give you an integer, because K plus L is an integer. So let's write this as K plus L is equal to C minus A divided by modulus. Now, since K and L are integers, therefore K plus L is an integer. K plus L is also an integer. What this means is that when we divide C minus A by M, we get an integer. So what can we write? M divides C minus A. And the reason we were able to write this statement is because we know it gives an integer, K plus L, which is an integer. So m divides c minus a. So what does that mean? The difference between c and a is a multiple of the modulus, which means then that a is congruent to c. So I'm going to write that down in a sentence. So as the difference between c and a, or a and c, so that's what c minus a is. It's the difference between those two numbers. As the difference between a and c can be divided by m. Okay, that means that there's no remainder, and it gives an integer. Therefore, it's spelled right. Therefore, A must be congruent to C under the modulus of M. Okay, now we get on to some problem solving questions, and we always tackle these in the same way. You'll get these questions where you've got big powers, big numbers like this. Our aim is to reduce the number into a smaller number that we can actually calculate easily, probably without a calculator. So using the modulus, mod m, congruent integers to reduce or simplify, reduce the integer to a smaller one. It's normally the technique we use in this question. Now, also in this question, one of the rules was that a to the power of n is congruent to b to the power n under mod m, and that's going to help us. So if we can find the power of a smaller number, it's going to be congruent to this power. So for example, if I could reduce this to 1 or 2 or 3, then it will be the same, congruent to this value. I'll show you what I mean. So let's start with 23. What's 23 under mod 11? Well, 23 in mod 11 is equal to, well, that's 11 times by 2, which is 22 plus 1. So there's a remainder of 1. So 23 is congruent to 1 in mod 11. So we'll reduce the 23 to basically a congruent value, which does the same thing, 1. So now we can use this rule here. So 23 to the power of 753 is congruent to 1 to the power of 753. Now, which one is easier to work out? This one. Right. 1 to the power of 753, well, 1 to the power of anything is just 1. So we've showed that 23 to the power of 753 is congruent to 1 in mod 11. And the way that we did that is that we said, right, okay, what number is congruent to 23? And that happened to be 1. So rather than do 23 to this big power, we just do 1 to the big power, because this rule says we can do that. Okay, so this question says find the remainder when this number is divided by 11. Now, anytime you get a question that says divided by something, let's call it m, you want to be working in mod m. Yeah, if a question says divided by a certain value, if this said divided by 5, we want to be working in modulus 5. The reason we do that, if we work in modulus 11, what does the number represent in modulus 11? The remainder. So that will give us the remainder. So the first thing we want to do is write out what is 343 in modulus 11. Right, now 343, let's divide it by 11 on my calculators and see what we get. So 343 divided by 11, that's 31. So this is 11 times by 31. If we work that out, that gives us 341. So there's a remainder of 2. Right, so 343 is congruent to 2 in modulus 11, mod 11, because they have the same remainder when divided by 11, and 2 is the easiest number. I mean, I could do add 11 to this or take away 11 from this to find other congruent values, but this is going to be the easy one. So what does that mean? 343 to the power 5 is congruent to 2 to the power 5 in mod 11. That's because we use that rule that says a to the power n is congruent to b to the power n under mod m. Now, which is the easy one to work out? Well, I can definitely work out 2 to the power 5. So 2 to the power 5, I think that's 32. That's 32. But now we need to change 32 to a mod 11 value to find a remainder. So 32 mod 11, 32 is equal to 11 times by 2, which is 22, plus 10. So there's a remainder of 10. So 32 is congruent to 10 under mod 11. That's the remainder. So remainder equals 10. So let's just write out the stages of the working here. So first of all, 343 is congruent to 2. Then we said 343 to the power 5 is congruent to 2 to the power 5. 2 to the power 5 is 32. And 32 written in mod 10 is congruent, mod 11 is 10. So that represents the remainder. Okay, this one says work out the final digit in this number. Now, whenever it doesn't say anything about divided by 5 or 6 or 11 like the last example, or under a certain modulus, it means we're working with normal numbers, which is modulus 10, because we work in sort of base 10. Yeah. So if no divisor or modulus is mentioned in the question, then we are using mod 10, because basically mod 10 is like the numbers that we use ordinarily, and that's basically what this question is about. It's an ordinary number. Work out the final digit in that number. So this is going to be modulus 10. So the first thing we're going to do is we're going to write that number in modulus 10. So we start with the 513. Don't start with the powers or anything like that. So 513 divided by 10, well, that's going to be 51 times by 10. Let's get rid of that for the minute. It's just equals. Then we'll write it in modulus 51 times by 10 plus a remainder of 3, which means 513 is congruent to 3 in modulus 10. mod 10. Now, in the previous question, what we would have done, that the power was small enough for us to work this out, or it was a number where the power was easy to work out. So if I've got 513 to the power 50, which is congruent to 3 to the power 50, 3 to the power 50 is still too big to work out. Okay, so too big to work out. So we need to find a smaller power of 3 that we can use. So 3, well, it needs to be something that goes into 50, for example. So here's just some things that we might want to try. So for example, 3 to the power 50, that's equal to 3 to the power of 5 to the power 10. Now 3 to the power 5 is 243. We can do that on our calculator. To the power 10. But that's too difficult. We're not going to be able to work that out. Even if we change this to modulus 10, which would be 3, that's going to be 3 to the power 10. That's still too big to work out. Okay, is there a different way we could do it? Okay, what if we did 3 squared? So 3 to the power 50 is the same as 3 squared, and then 3 squared to the power 25. Now 3 squared is 9, so 9 to the power 25. Now 9 written in modulus 10 would be, well, it's congruent to -1, isn't it? So if I take 10 away from that, I get -1. And I can do -1 to the power 25. Yeah. By doing it this way here, the problem was I can't find a congruent number that's small enough to work out to the power 10. But this way I can. So what we'll do is we'll just state here that 513 to the power 50 is congruent to 3 to the power 50. We can't do 3 to the power 50, it's too big. So we're going to do 3 squared. Now 3 squared is 9 in mod 10, and 9 is still too difficult, but 9 is congruent to -1. So where I've got 3 squared, and I'll do that to the power 25, that's congruent to 3 squared is 9, which is congruent to -1. So -1 to the power 25, all under mod 10. So now I've got a calculation I can do. -1 to the power 25, well, that's just going to be -1. So -1 to the power 25 is equal to -1. And -1 under mod 10 is 9. Because -1 is the same as 10 times by -1 plus 9, that positive remainder. So what's left over after we do this calculation? 9. So the remainder equals 9. Now you might find these types of questions difficult because everyone is different. There's not like a method that you can say, right, this is always going to work when you do this question. But what you may find helpful is to try and simplify the question to a calculation that you can do quite simply. Yeah, we're not going to be working out these huge powers. So rules of powers might help. Find these congruent numbers as you work through the calculation. So after each step, is there a congruent number you can change it to that's much easier? And then that will allow you then to make the question quite easy to do. Now you'll notice that we ended up with negative 1 to the power 25, and I think on example 15, I think it was, we ended up with 1 to the power of 753. So notice how we end up with 1 or negative 1 to a power. Yeah, that may give you some hints as to steps you might take to actually work out an answer. Okay, so this question says find the remainder when 19 to the power 273 is divided by 12. So as soon as you see divide by 12, divide by something, it tells you what modulus you're working in. This is going to be mod 12, and whatever remainder we get at the end is going to be the remainder that's going to give us the answer. Right, so 19 to the power 273 is what we want to find the remainder of. So step number 1, can we find congruent values to 19 which are simpler? Right, okay, so we can just take away 12, so that will give us 7 is congruent to that. If we took away 12 from that, that gives us minus 5 is congruent to that, all under mod 12. So maybe the 7 or the minus 5 are numbers that we can work with. Right, so like the previous example, let's see if there's anything we can do with these values here. So 19 to the power 273 is going to be congruent to 7 to the power 273, which is congruent to the power negative 5 to the power 273. Now obviously we can't work out the power 273. Is there an easier power that we can use? Now notice that 273, the power, can be divided by 3, and that gives 91. Okay, let's try this. It may not get us anywhere, it may not work, but let's try and see if this works. So right, if I worked out 7 cubed, yeah, so 7 cubed, that's the same as, or 7 to the power 273, 7 cubed to the power 91, or even if I tried this. So again, don't really know if these are going to work. They may not do. Right, 7 cubed is 243. And 243 written in mod 12 is going to be 3. So you've got 3 to the power 91, so not really anything we can do with that. Over here we would have negative 125 to the power 91. So if we wrote 125 to the power in mod 5, oh sorry, mod 12, that would be negative 5, because negative 120 plus 5, sorry, to the power 91. Again, nothing we can really do with that. So doing it this way is not going to help. And we don't really want to go to 7 to the power 4, 7 to the power 5. So let's try 7 squared. Right, so 19 squared is going to be congruent to 7 squared. And 7 squared is 49. And 49 in mod 12 is going to be 1, because you've got 4 times 12 plus a remainder 1. So 49 is congruent to 1 in mod 12. Now this is more useful, getting the 1 here. So putting this all together, what we've got is 19 squared is congruent to 1. Now we want to try and get up to the power 273. And we can't do that by doing a whole number power to each side. We can get to the power 272, which is because we've got an even power. So I could say 19 squared to the power of, that would be 136, is then congruent to 1 to the power of 136. So that tells us that 19 to the power 272 is congruent to 1. which is useful. So if I want 19 to the power 273, what I need to do is times both sides by 19. So 19 to the power 273 is congruent to 1 times 19, which is basically 19. So 19, 273 is congruent to 19. And we're dealing in mod 12, aren't we? So really I should have put mod 12 up over all of these. And 19 is congruent to, take away 12, 7 in mod 12. So that's the remainder. So the remainder is 7. Okay, so in this question it says find the remainder when the sum of all these factorials from 1 factorial to 100 factorial is divided by 15. So whenever you see the words remainder divided by something, it tells you mod. So this question is going to be in mod 15. So let's start by writing out what the sum of these factorials is, because we haven't got a formula where we can simplify it. So we're going to have to write them down. So 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial. And we're going to go all the way up to 100. Obviously, I'm not going to write those out. It's going to look like this, plus all the other factorials afterwards. Now notice that when we get to 5 factorial, we've got times 3 and we've got times 5. What does that mean? It means that it's divisible by 15, divisible by 15, which means that 5 factorial is congruent to 0 under mod 15. There's no remainder. And that's going to be the same for all the other factorials after, because they're all going to have times 3 in there somewhere and times by 5. So they're all going to be divisible by 15. So I could write down that from 5 factorial to 100 factorial, they all contain times by 3 and times by 5. So they will all be divisible by 15. There'll be no remainder. So that means that the sum from 5 factorial to 100 factorial will also be divisible by 15, which means under mod 0 or mod 15, the remainder is 0. So you've got a multiple of 15 plus another multiple of 15 plus another multiple of 15. The sum of all of these multiples of 15 will also be a multiple of 15, which means there'll be no remainder. So all that's left is working out 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial. That's all that's left. So that's going to be 1 plus 2 plus 6 plus 24. If we work that out, that will give us 33. Right, now we need to work out what the remainder is. So 33 is equal to 15 times 2 plus 3, so there's a remainder of 3. So 33 is congruent to 3 under mod 15, which means that the remainder is 3. So that'll be our final answer. So you should now be able to do exercise 1C on pages 14 to 15. Just a recap. So this modulus m thing that we were doing is basically the remainder when you divide by m. There are rules that we can use for these modulus type questions. If the modulus divides an integer, what that means is that that integer is going to be congruent to 0 under the modulus of m. Every integer is congruent to itself, again under mod m, for any integer value of m. We can write an integer or a congruency relationship, we can write it either way round. We can link them together, so these are all mod m, by the way. So if a is congruent to b and b is congruent to c, it then follows that a is congruent to c. We prove that. And these last set of rules here are where we have congruency between pairs of numbers. Let's call them a, b and c, d. So the rules are, we can add or subtract, let's get the right symbol there, a and c, and that will be congruent to an addition or subtraction of b and d. You can think of that like the addition rule, and then the multiplication rule. Multiplying a and c will be congruent to b and d. We can multiply both sides of the congruency, so we can do a multiple of a, that will be congruent to a multiple of b, and the last one to do with powers will be a power of a will be congruent to a power of b. So my tip to you when doing these questions is just try and reduce down the numbers in the calculation, particularly if they're big numbers, big powers, to smaller congruent integers.